Okay, so so this is horizontal composition, and in the traditional view, very complicated, right? But now let's simplify this thing and draw the string diagram for this. So now we have three categories, C, D, and E. So there will be three areas, right? So here's the diagram. We'll have three areas, C, D, and E, corresponding to these three categories, right? Now we have from functor f to f prime, there is a natural transformation alpha. So alpha will be here, right? This will be f, this will be f prime. Okay, well I can put these things outside. So this line corresponds to f, this line corresponds to f prime. Alpha is a natural transformation from f to f prime, right? Everything works nicely. F from C to D, f prime from C to D. Now from D to E we have G and G prime. So this will be G, this will be G prime, and the natural transformation is the dot in between. Okay? And that's it. This is beta circle alpha. That's the horizontal composition, right? So you read it by it's like scanning it from the bottom and say until you hit the dots, okay? And then you say hit the dots and you say, oh, this is beta after alpha, horizontal composition, right? And what is it connecting? Well, it's connecting this composition of G after F to the composition of G prime after F, right? Because this stripe here is G after F, this stripe here is G prime after F prime. So how to compose functors, right? And now the magic of these string diagrams is that it's like you might be wondering, okay, is this beta really at the same level as alpha here, or is it a little bit higher than alpha, right? It's like easy to make a mistake here. Oh, right? So the important thing is that I can move these dots. Okay, I can draw this beta here and this alpha here, and it will still work. Okay, so the actual position of beta and alpha doesn't matter, and this is because of the interchange law. Okay, so the interchange law says that if I have, and this is something that will be really difficult to draw as well, maybe as a diagram like this, it's not that hard. Drawing something like this would be really hard. But the interchange law says that if I have four natural transformations, okay, alpha, alpha prime, let's say beta and beta prime, okay, I can interpret this, so I could label these, this is F prime, F double prime, maybe, right? So F prime, F double prime, this is G prime, G double prime, okay? Now this is kind of ambiguous, right? Because I can say, okay, I'm scanning it from bottom to top, right? So first I have a horizontal composition of beta after alpha, right? Horizontal composition, that will be my circle, beta after alpha, right? And then I continue scanning, so means I'm composing it vertically with another one, which is beta prime after alpha prime, composed horizontally. So like I draw this horizontal line here and another horizontal line while my scanning goes on. So this is it, right? And these two are composed vertically. So first this one and then this one. right? But I can also compose them, interpret this differently. I could say, well, what is this? Well, this is alpha prime composed vertically with alpha, right? And this is beta prime. Well, so I'm going to write it here, okay? So alpha prime, alpha, and this is beta prime after beta composed vertically. Okay, so I have now shrunken these to two natural transformations. One is this and one is this, right? And I'm composing them horizontally, right? And these two things better be equal, okay? This is called the interchange law. And it's very important. Okay, so this is a theorem that can be proven using naturality. You can actually prove that this is true for functors and natural transformations. But in general, if you want to use string diagrams for some other purposes, and I'll show you in a moment what are other purposes, then if you want to use string diagrams, then this better be true. Okay. So this is the interchange law. Now, if I have the interchange law, then I can go here and I can say, okay, so let me interpret this. Okay, I can interpret this as scanning from bottom to top. Okay, what is this? Here I have alpha, but here I don't have anything. Okay, this not anything, that's identity natural transformation. I can insert an identity anywhere I want, right? So this is really identity after alpha. And here's the notation that's used because you can insert identity anywhere on a line. This is a G line here, right? This is an F prime line. Because I can insert identity on the G line, this is actually called G. Okay? Instead of saying IDG, so one way of saying would be IDG, right? Natural transformation from G to G. The notation for this in mathematics is just say I'm composing G with alpha. So this is the horizontal composition, so this is this, right? So this is G after alpha horizontally, right? And this is called whiskering when you are inserting the identity here. So when you see something like this, when one of them you know it's a natural transformation, but the other is a functor, how can you compose functor with a natural transformation? The only way to understand this notation is that this is really representing an identity natural transformation on G. Okay? So there's no ambiguity. Okay? So I have G after alpha, and here I have beta after F prime. Right? Because this is an F prime line. Correct? Correct. Yes. So this is G line, this is F prime line, right? And by interchange law, okay, this is equal. The other interpretation is simply, well, it's just beta after alpha, right? Because this is identity, this is identity. It's like if you put right, if you substitute identity, that's what you get. Right? So this is called whiskering, and this lets you like move these alphas and betas up and down whatever way you want, right? Did I do it right, or this is circle? This is circle. Okay. Correct me, okay? because has to be the same as if I had beta and alpha on the same level. That would be circle, right? Okay. Okay, whiskering interchange. Okay, now monads. Monads. So what's a monad? So a monad, it's like in Haskell, right? It has this return. In mathematics, mathematicians call it eta. What we call return, they call it eta. And eta is also, so let me write return. Return goes from A to, and I will call this functor. I mean, a monad is a functor, right? We usually call it M. Mathematicians call it T, just to make it interesting. Okay, so so in Haskell we would say M, right? Here we'll say T. Okay, so the component that this looks like this is for all A. It's a natural transformation, really, but it's a natural transformation from the identity functor, right? Identity functor acting on A is just equal A. So eta is a natural transformation from identity functor to T. Okay, so instead of M, I'm writing T. So we have a functor, identity functor, and we have this functor T, which is our monad. And the other one, which we call join, right? Join goes from MMA to MA, right? And mathematicians call it mu, and they say it goes from T composed with T to T, right? So the component of this at A is exactly this, right? So I act with M first on A, and then on this result I act with M again, right? So here I act with T on A, and then another T, right? So this is a composition of functors, so it's like the square, right? So these two natural transformations define a monad. Well, plus laws, of course, right? So we'll get to laws. So how would we draw this as a string diagram? Well, these are natural transformations. We only have one functor here, right? And it's actually an endo-functor. So we don't have to really mark the category, it's just one category. But an endo-functor, well, an endo-functor will be just a vertical line, right? So, and this is the same category, C and C. So this is going from C to C, an endo-functor, right? This says I have a natural transformation that goes from identity. Okay, so how do we could draw the identity functor as sort of dotted line, right? And sometimes people do this and say, and this is T, right? So this is a natural transformation. This is the same category, C, right? So I have two functors. One is identity from C to C, and the other is T from C to C, right? And here's a natural transformation that goes from identity to T, right? So what normally we do is and this is called eta, right? We don't even draw this line. Why should we draw this? I mean, we can draw an identity functor anywhere we want, right? It's like we can insert an identity functor here or here, you know, anywhere. It does nothing. So it's just like multiplication by 1. We don't even have to draw this. So this is this is what we call the return here. Here it's called unit. So this is unit. Eta is unit. Now this thing, okay. So at the bottom it will be a natural transformation mu going from T after T. So So we'll have to have T and another T, right? So composition of T with T, right? At the top, we have a single T, okay? So a natural transformation goes from this stripe, T after T, to this single line, right? So how do we draw this? Well, we draw it like this, you know? This is our mu. Okay, it connects this stripe T after T to this T. And that's our mu. Okay? So that's a monad. A monad has these two things, plus the laws. Okay, so what are these laws? Okay, so the laws there's a unit law which says, like, if you think of this as multiplication and this as unit, okay? So maybe I should digress a little bit and talk about monoids, because of course a monad is a monoid in the category of endofactors, right? So a monoid is defined in a monoidal category. And in a monoidal category, you can draw, what do you have in a monoidal category? You have a unit object, okay? That unit object, and you have a way of multiplying objects. It's called a tensor product, okay? So what you can do using string diagrams, you can draw diagrams in monoidal category by using the tensor product horizontally. So if you have two objects, let's say M and N, right? You draw them as line. So now objects become lines. Previously objects were dots, right? Now objects are lines. Right. So this is a diagram that corresponds to N cross M, the tensor product. Okay. So this is very similar to what we were drawing for our functors, except that now I'm saying this is a tensor product of two objects. What's the connection? Well, in a functor category, objects are functors, and tensor product is composition of functors. So this works exactly the same way in an arbitrary monoidal category, and in particular it works in a functor category. So all the stuff that I told you about functors and string diagrams in the functor category, that's just because a functor category is a monoidal category. It has multiplication of objects. Objects here are functors, right? And morphisms in a monoidal category will be dots, okay? So if, like, I have object M and that's M prime, let's call it, okay? So I can have a morphism from M to M prime. And I can put it here, like this is F, okay? And again, you know, it's like a morphism in the category, in the functor category, is a natural transformation. So this is why I was using natural transformations here. But this works only in an arbitrary monoidal category. So in a monoidal category, how do you define a monoid in a monoidal category? Well, first of all, you define two things. You define a unit, which is a morphism that goes from the identity, the unit object in a monoidal category, to this object M, that's your monoid. And you have multiplication that goes from M times M to M, right? Now you recognize this as multiplication, right? It's like multiply M times M, you get M, right? So this is actually this picture in a monoidal category, and this is this picture in a monoidal category, right? With a tensor product, which is just a, right? Okay, so so this is a little digression, so that you know that this doesn't come from nowhere. It comes from monoidal categories. If you work in a monoidal category, you can use string diagrams. But we are now interested in this particular monoidal category, which is the functor category. Okay, so the unit it just says that if you multiply using mu with eta as a unit, you should get back the same thing, right? So it's a diagram that sort of goes like this. This is my multiplication, and this is my eta. Okay, I start with t and I end with t. If this is unit, then this should be equal to this. Okay? So I can sort of like pull these two strings. This is why it's called string diagrams, because you can take these strings, pull them, and this eta will be like absorbed. Right? Special side effect. So a sound effect for this. You know, pull this, and eta is absorbed, and you get this. Right? So I mean we can write it as it's like this. So if you scan it from the bottom, this is t horizontal with eta, right? At this level. Then we get mu. And this should be equal it t, right? So this natural transformation is equal to this natural transformation. So that's the right unit law. Now you see why it's right, because unit is on the right. There is a left unit law in which eta is on the left. And of course there is this associativity law, right? Associativity law, which looks like this, right? So you have t, 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 and a single t here, and this is mu, and this is mu, and this should be the same as if we first multiply these two and then multiply these two, right? So, 2 unit laws, 1 associativity law, beautiful diagrams. And now if you have these laws and you have some complex diagrams, you can always manipulate them by using this, by pulling these strings. You know, like how do you get this? I mean, you pull this down, you pull this up, and you get this, right? So, topology. Okay. So this is the monad. What should I leave here? So I want to now go to adjunctions, okay? Adjunctions. So remember this, memorize this stuff. Okay, I don't need this anymore. Adjunctions. So adjunctions, what's an adjunction? Well, it's sort of, you have two functors that go between two categories, right? So you have some category C and D, right? And you have a functor, let's call it left, and another functor, let's call it right, okay? And it's sort of like these functors are not really the inverse of each other, but close enough, okay? And the definition of adjunction is that if you take any object here, and you'll get LA here. You take any object B here, you get RB here, right? That the homesets, the morphisms, going down. So the way to remember is that the morphisms always fall down, like rain from this. This is the left one, this is the right one. That these morphisms are in one-to-one correspondence. Right? So for every morphism here, there is one here. And for every morphism here, there's one here. There's exactly the same number sort of morphisms, which means that there is a bijection between these Hom sets. Right? So this Hom set here, well, let me draw this Hom set first. I mean, the notation for this, a Hom set from LA to B is isomorphic to the Hom set from A to RB. Okay? And now, so this doesn't look immediately like it would be something that you can draw with string diagrams. Except that there is another formulation of adjunction that's based on unit and co-unit, and it works like this. Since this is working for every A and B, and in fact it's natural in A and B, okay? So this is like an additional thing. Oh, okay, you have to check that this is natural in A, natural in B. Okay. So because it works for any A and B, I can say, let me pick, let's say B that's equal LA. Okay? Why do I want to pick this? Well, because then I'll get LA to LA here, and here I get A to R LA. Okay? Now this Hom set from LA to LA, it's the same object, right? I know that there is one member there, for sure, always. That's the identity, right? Identity on LA. So corresponding to this identity, there has to be something in here. Okay, and this something in here, it's a morphism that goes from A to R L A. Okay? And it has to be uniform in A, it has to be natural in A. So in fact it's a morphism. It's a natural transformation, right? Because it works for every A, right? Every A. Okay, so I can write it as a natural transformation between identity functor and R after L. Okay? And I will call this eta. Okay? Just like before I called this other thing eta. Right? And I can do the same trick, but on the other way around. I can say, let me pick A equal RB. Okay? So now I have C RB RB, which I know has an identity at RB, right? And this has to be D L, A is RB, so RB, okay, B. Okay, so here the identity will correspond to a morphism from LRB to B, which is natural in B, okay? So this is a natural transformation, and I will call this epsilon, that goes from LR to identity functor acting on B, right? So I have these two things. So instead of defining the adjunction using Hom sets like this, right, as a natural transformation between Hom sets, we can define adjunction using these two natural transformations, which are called unit and co-unit. Okay, and this is a completely equivalent definition of adjunction. But this one is more like in the spirit of adjunction being the inverse, one functor being the inverse of the other, right? If these were the inverses, then RL would be equal to identity and LR would be equal to identity, right? That would mean that L is the inverse of R. They are not, because these natural transformations go only one way and this one goes the other way, okay? So it's not fully inverse, but it's sort of close to the inverse. It's sort of like the best approximation to the inverse that we can get, right? And the standard example of an adjunction that we as programmers always use is currying. Currying is an adjunction between a functor. Here we will say A, comma C. So these are functions from a product of AC to B, and these are functions from A to the functions from C to B. Okay? So function type is the right adjoint of product. Okay? This is something I talked about in the previous, but you can look it up. So this is the very important adjunction that we as programmers use all the time. Okay? Thank you.